Okay, hello everyone. My name is Anudh Mishra and I am an MBBS student at AIIMS Bhuvneshwar. Today we are going to see the chapter Chemical Kinetics. This is the chapter of your physical chemistry class 12th and basically it holds a good weightage for JEE-Main. We are going to cover this chapter keeping JEE-Main in our point of view because we are basically preparing for that. So I'll keep that in my mind while explaining this chapter to you. First, I'll do a brief explanation, after which we will start with the previous year questions of JEE Main. Okay, so moving to the definitions, what is chemical kinetics? Chemical kinetics is basically study of speed of reaction. And previously in our courses, we have covered topics like equilibrium and thermodynamics. So what equilibrium does, like, see, the feasibility of a chemical reaction, how will a chemical reaction occur or not, this question is answered by thermodynamics or your Gibbs free energy. Feasibility, after the feasibility you will check how much the reaction will proceed or extent of the chemical reaction. This will be determined by equilibrium constants or equilibrium of the reaction, and we have seen this in the chapter equilibrium. This chapter will attempt to answer the question how fast the reaction is going to attain equilibrium or speed of the reaction. That is answered by chemical kinetics. Got it? This is what chemical kinetics is about. So let's start our discussion. And firstly, we'll see what a rate of a chemical reaction means. My advice to you is read NCRT for all the chapters. Do not rely on any other material, at least for JEE Main, because sometimes you get direct questions from NCRT and it helps a lot. Those questions are really easy. You should not lose marks in those questions. So for that, I'm advising we should see things from NCRT. How does NCRT define the rate of a chemical reaction? See, it says the rate of decrease in concentration of any of the reactants or the rate of increase in concentration of any of the products. Right. Then this is the definition of rate. They have considered a hypothetical reaction and they have given the rate as decrease in reactants concentration and they've given rate as decrease in concentration of reactant divided by time taken or increase in concentration of product divided by time taken. Okay. Since delta R is a negative quantity, it is multiplied by -1 to make the reaction a positive quantity. We don't need to rely on that. This graph is important. They might ask what is instantaneous and average rate. For instantaneous rate, use the slope, and for average rate, use the change and divided by change in time. Okay, both of these slopes. Okay, this is concentration of reactant, this is concentration of product. Use the same concept to find out the rate in both of them. Okay, moving on, units of rate. Basically, what units of rate are? The units of the rate will basically be the same units which is for the concentration divided by the unit of time. Okay, unit of concentration is mole per liter, unit of time will be second, so the unit is mole per liter per second. If the concentration is expressed as a pressure for gases, it is atm per second. No need for us to go here. They have given a graph and they have defined rate at different time intervals, instantaneous rate. Generalizing that, generalizing this term, they are explaining about factors influencing rate of reaction. So first factor is basically concentration. This law is known as rate law. Okay, the dependence on concentration and rate law, you need to understand. Consider this general equation and try to understand. This is the general equation. Rate is proportional to a raised to the power x and b raised to the power y. Now this x and y are both variable. It is not equal to the stoichiometric coefficient. Okay, just as you do in equilibrium, it is not equal to the stoichiometric coefficient. It is something different. So what is this x and what is this y? The x and y are determined experimentally. This is known as, okay, they have not provided it properly. Just remember this equation. Rate is some constant into a concentration of a to the power x, b to the power y. This k is rate constant, k is a proportionality constant called rate constant, and the x and y are determined experimentally, okay, raised to some power which may or may not be same as stoichiometric coefficient of the reacting species. It is raised, the thing which is, it's raised to some power, right? And it may or may not be equal to your stoichiometric coefficient. Then initial rate of formation of NO2, for this equation they have defined x to be 2, y to be 1. Here it matches their stoichiometric coefficient, but there are examples. For example, look at this one. Look at this one. Here the stoichiometric coefficient of chlorine is 1, but the power to which it is like raised is 1 by 2. So it may or may not be same. Anyways, what is the order of the reaction? Order is sum of the powers of concentration. So order is basically what? X plus y. Nothing more to be remembered. Okay. Order is nothing more than x plus y. It is the same. Then units of rate constant. So this is a bit complicated. You cannot calculate it just by that. Either you remember this unit, okay, where n is equal to x plus y. You remember this unit, or you just basically more easy to use this equation. Just try to find out using this. Like, it is always better to start from the basics. If x plus y, see, the unit of rate constant is variable for different order of reactions. If x plus y is equal to 1, okay, then your rate will be, unit of this rate constant will be basically the unit of your time inverse. So unit will be second inverse. If it is 2, then unit will be second inverse moles inverse liter. Okay, this is how you're going to find out. They have given a table, so no need to mark up the table. Okay, use this equation and find out the rate constant. I'm still underlining this for you, but I would advise you to always rely on the equation itself to find out the rate constant. What is molecularity of the reaction? Molecularity of the reaction is the number of reacting species taking part in the elementary reaction, which must collide simultaneously to bring the chemical reaction. This is again, it may or may not be same to the order of reaction. Why? Because look at this. The molecularity of this reaction is what? This is a unimolecular because only one molecule is involved. So this is unimolecular. For bimolecular example, 2HI gives H2 plus I2. Trimolecular, see, 3. There are not like tetra, penta, and etc. They usually are not seen. Why? Because the probability of more than 3 molecules which can collide simultaneously in a reaction is really small. So hence reaction with molecularity 3 and more are rare and they are slow. Suppose this reaction. Consider this reaction. Here If you add up the stoichiometric coefficient, it will be your something like 10. Okay, but the molecularity is not equal to 10. It is less than 10. It is a second order reaction. Okay, which shows that this reaction takes place in several steps. Now, which step is important to us? The step which controls the molecularity. It is called rate determining step. Considering another example, writing the rate law. Now, this reaction is a first order reaction. It takes place in two steps. What is the rate determining step for this reaction? Both the steps are bimolecular elementary. Species is called an intermediate. It is formed during the course of time. You don't see IO minus anytime else. Thus, the rate of formation of intermediate will determine the rate of this reaction. So, till now, we have learned three terms: rate, which you all know, no need to explain this. Rate, constant, also you know, no need to explain this. Order. Order is x plus y, whatever power you are raising. Molecularity, variable. Again, both of them may or may not be equal to stoichiometric coefficients. They have also summarized it. Order of a reaction is experimental. It can be zero, fraction. Molecularity cannot be zero or fraction or non-integer because molecularity is what? Molecules. And they cannot be zero or in fraction. Got it? Next point says order is applicable to elementary as well as complex. Molecularity is only applicable for elementary reaction. For complex reaction, molecularity has no meanings because it occurs and complex reaction occurs in elementary steps. For complex reaction, order is given by the slowest step. Molecularity of the slowest step is same as the order of the overall reaction. These points you can remember. Integrated rate equations. No need to remember how they are achieved. Just remember the equation. For zero order reaction, this is basically the equation of concentration of reactant. So reactant concentration at any time is given by initial concentration minus K into T. K is your rate constant. Moving on. Okay, we have a table at the end, I think, as far as I remember. Half-life. We have a table at the end. So I'll just explain zero and first order using this table. Okay. We move on to half-life. We'll see what a half-life is. But first, let's see what is the reaction type. Reaction type is reactant turns to product. Nothing special here. Differential rate law means change in concentration divided by time. Okay. dr by dt. And for zero order reaction, it is equal to minus K. And for first order, it is equal to minus K initial concentration of reactant. Or sorry, this is not initial concentration. This is concentration of reactant at that time. So can you understand what is happening at first order? In first order, the rate of reaction is proportional to the concentration at that time. Means if the concentration is really high, the rate is also high. But as it progressively decreases, it turns into product, the rate also decreases. This is first order. For zero order reaction, it does not depend on the rate, it does not depend on the concentration, it is constant and it is equal to the rate of the reaction or rate of change of concentration is equal to minus K. No dependency here. Next, integrated rate law, which we just saw. Change in concentration is KT. For this, you have to take logs here because it is instantaneous. So yeah, the reactant at any time t is the concentration of reactant at any time t is initial concentration of reactant e to the power minus k t. Okay. Then straight line plot will be obtained when you give r concentration versus time. Here, natural logarithm of concentration versus time. What is half-life? Let's see what a half-life is. So half-life definition we all know: time in which concentration of a reactant is reduced to one half of its initial concentration. This is half-life. For a zero order, the rate constant is given by, forget the rate, they're just writing the integrated rate law. K is R naught minus R divided by T. So at T half-life, R is equal to 1 by 2 R naught. So yeah, this is the formula for half-life of zero order reactions. For first order reaction, this is the K. Again, at T 1 by 2 or half-life, it will be R naught by 2. Above equation becomes this. So yeah, this is the, or you can simplify this further this. This is the formula for T, half-life of a first order reaction. This ln 2 by k is 0.693 by k. Units of k they've given. Just remember it. So this table is good. You can take a screenshot of this table, keep it for future because you'll be using this. Now pseudo first order reaction, nothing. It's a theoretical concept. Look at this reaction. It should be a second order reaction because it is bimolecular. Okay, but concentration of water does not get altered much. So concentration of H2 is constant. So rate equation becomes this. Nothing much special about this, just an exception. Next, after pseudo unimolecular, we have temperature dependence of the rate of reaction. So for experimentally, it is found that if you increase the temperature by 10 degree, the rate constant is nearly doubled. The exact equation of dependence of rate constant with temperature is this. It is the Arrhenius equation. A is the Arrhenius factor or frequency factor. It is also called pre-exponential factor. Blah blah blah. R is gas constant. EA is activation energy measured in joules per mole, not kilojoules per mole. Please remember, it's joules per mole. Now, what does Arrhenius say? Arrhenius say that formation of intermediate happens. He gave this graph. This graph you have seen a lot of times. This graph is basically used to explain activation energy. Yeah, this delta H, it might indicate endothermic or exothermic reaction. Here it is an exothermic reaction. But yeah, now the if you have read KTG, this is the kinetic energy and number of molecules. The most probable kinetic energy lies somewhere here. And what happens if you raise the temperature is this curve flattens and broadens out. Okay. So if you just randomly draw a line, this is a dry this then the molecules, as it is broadening out, you can see in the curve, the molecules with kinetic energy equal to or more than this will be increased additional when you increase temperature because the curve is going to flatten and broaden out. That was the theoretical explanation. Some modifications of the reaction: you take ln on both sides, you get this equation. So graph between L and K and 1 by T. Slope will be equal to this. Intercept is L and A. That was about the graph. Comparing the rate constant in two different equations. If you compare it for two different equations, you get this. This is the, for different temperatures, you get this equation. Okay, you get this equation, right? Nothing, just remember this. Remember this equation. You will be using this a lot. They'll give you a lot of questions based on this. Okay. Effect of a catalyst. Now we come to the theory part. Okay, we have just theories right now. We can end the chapter and then move on to the questions. Just let's finish. Effect of catalyst. We all know what a catalyst does. Okay, the catalyst, basically it lowers the activation energy, that we all know. Some common mistakes that are made here is people assume that catalysts like they alter the equilibrium, they like make it favorable for the product. No, the catalyst do not involve themselves with the equilibrium itself. It is just involved in the speed of the reaction. So yeah, attaining equilibrium becomes faster if you use a catalyst. Never say that catalyst will make more product. Catalyst does not make more product. Catalyst does not alter the equilibrium, it cannot do so. Okay, it depends only on the temperature, how much product will be formed. Only and only how fast the product is going to form is determined by catalyst. Yeah, some industry, like all the industries, exploit this effect of catalyst. Just a second. Yeah, continuing. Although all the industries exploit this use of catalyst, that catalyst can form products faster, what they do is they keep removing the products so that the reaction never reaches equilibrium. They keep adding catalyst, they keep removing the product. Catalysts make the equation reaction fast. Okay, they are trying their best to reach equilibrium, but since they are removing products, they are not, the reaction is not reaching equilibrium properly. So basically that is how they exploit it. But naturally what happens is catalysts, they just speed up a reaction. They just reduce the activation energy, which automatically decreases the amount of energy needed to do a reaction. Example they have given, this example, catalyst is MnO2. So yeah, the word catalyst should not be used when added substance reduces the rate of reaction. This is evident. We all know this because the substance then is called an inhibitor. Intermediate complex theory explains the catalyst. See, activation energy with a catalyst, activation energy without a catalyst. Which is more? Without a catalyst. So yeah, reaction path with catalyst is more feasible. Okay. And it is also clear from Arrhenius equation that lower the value of activation energy, faster will be the rate of reaction. So yeah, if activation energy is being reduced by a catalyst, reaction is getting faster. Moving on, small amount of catalyst can catalyze large amount of reactants. Catalyst does not alter Gibbs energy. Catalyst does not alter, it does not catalyze non-spontaneous reaction because it cannot form equilibrium or it cannot alter equilibrium, right? It helps in attaining the equilibrium faster by catalyzing forward and backward reaction to the same extent so that equilibrium state remains same but it is reached earlier. Yeah, this line you can remember every time you have confusion, that what is happening, product is getting formed or reactant is getting formed, both are getting formed at much faster rate, equilibrium is getting attained fast. Okay, moving on to the collision theory of chemical reactions. Though Arrhenius equation is applicable under a wide range of circumstances, collision theory is by far, I think it is the it is the most accepted theory. Yeah. So what was the problem with Arrhenius equation? Okay, what was the problem with Arrhenius equation? Arrhenius assumed, what Arrhenius said was that suppose this is a product, okay, it is composed of A and B. This is how the product looks. Imagine how the reactants would look. Nothing much difficult. This is A. I'm so sorry. This is A and this is B. Something like this they look. And if they fit perfectly like this, they will form the product. This is what Arrhenius assumed. He was really correct. Only if they fit perfectly like this, they will form the product. But he assumed that all collisions are going to be perfect. All collisions will bring these reactants near to each other in the same manner. But actually, that does not happen. Why? They might collide like this. They might collide like this. Okay. This will not form the product. They might get collide like this. This will not form the product. Only the correct collision will form the product. Okay. So the first factor which the collision theory says, the essence of collision theory is effective collisions. Okay. It says that collision in which molecules collide with sufficient kinetic energy and proper orientation form products, and they are called effective collisions. So only effective collisions like these will form products. Okay. Now some factors which affect, they have mathematically described them as number of collisions per unit volume is known as collision frequency, that is Z. Yeah, that is Z. Okay. So this is the second factor which accounts for effective collisions, that is P. So you multiply P and Z, you get the revised Arrhenius equation, or rate is equal to Pz E raised to the power A by RT. Thus, in collision theory, activation energy and proper orientation are required as a criteria for effective collision. So three criteria are there: activation energy, orientation, and effective collision. Got it? Good. Moving on to the exercises or the previous questions. The first question says number of correct statements. First statement is larger the activation energy, smaller is the value of the rate constant. So this is a correct statement. How do you explain it? From Arrhenius equation, and generally we can also explain it. Rate constant is inversely proportional to your activation energy, because if activation energy is more, the reaction is basically not that feasible. Got it? If it is more, it's not that feasible. Yeah, if it is less, then the reaction will try to happen. The second one is the higher the activation energy, higher is the value of temperature coefficient. So what is temperature coefficient? Temperature coefficient is how much change occurs if per 10-degree rise in temperature. Usually it is 2, like the reaction doubles itself. But higher the activation energy, it should be, the temperature coefficient should be lower, because for 10-degree of raise of temperature, it will be insignificant, because activation energy is so high that changing the temperature just by 10-degree won't do much of a increase. So temperature coefficient should not be high, but it should be lower. At lower temperature, increase in temperature causes more change in value of rate constant than at high temperature. This is like completely true. If you take, like if you observe a reaction at, suppose the reaction is happening at minus 15 degree Celsius. Okay, and you take it to some 15 degree Celsius. This is basically kind of your room temperature. Let's assume room temperature only 25 degrees Celsius. So assume a minus 15 degrees Celsius reaction happening at 25 degrees Celsius. So fast. It will occur so fast. But at the same time, there is a reaction. Suppose melting of a metal which occurs at 5000 Kelvin, or let's assume degrees Celsius only for the sake of convenience. 5000 degrees Celsius, you increase it to 5025 degrees Celsius. Will there be any significant change? No. It's almost the same. 25 degrees Celsius doesn't matter. Raise it by 40, doesn't matter. 5040. Here you increase it by 40 degrees Celsius and it just shows phenomenal growth, but here not that much. So yeah, this statement is absolutely correct. D says a plot of ln k versus 1 by t is a straight line with slope equal to minus ea by r. Yeah, we just saw it. So yeah, three of them are correct. Now, a student studied the decomposition of a gas AB3. He obtained the following data. He obtained the data. The pressure he has obtained, assuming the reaction is something like this. The reaction is something like this, and it is a unimolecular. Order we don't know, but we can see that there is only one molecule. It is unimolecular because yeah, like molecularity cannot be fraction or zero. Now let's see change in concentration of reactants. They have given pressure was, if pressure is 50, then half life is 4 seconds. If pressure is 100, then half life is 2 seconds. Pressure is 200, half life is 1 second. Coming back to the formula of half life, is, let's assume this is a zero order reaction. For a zero order reaction, your half life will be constant. It won't change with the concentration. So this is not a zero order reaction. So this is wrong. Assuming this is the first order reaction, 0.693 by K. This is also, wait, something is different here. For a zero order reaction, Kt is R not minus R. At T half life, it is R by 2. And T half life is, yeah, R naught by 2K. Yeah, for zero order reaction, this is the T half life which is directly proportional to your initial concentration. So on increasing the concentration, your half life should increase. But here we are seeing on increasing concentration, half life is decreasing. So this is not the answer. It cannot be a zero order reaction. For first order reaction, half life is independent of initial concentration. So this is also not the answer. 0.5, not the answer. So yeah, only one option is left. By eliminating, we reach the answer is order is 2. Next, the variation of rate of an enzyme catalyzed reaction with substrate concentration is correctly represented. Variation of rate with substrate concentration. As you increase substrate concentration, rate should increase. Okay. But only till some extent, after which it will become stagnant. So graph C looks the most correct to me. Next question says, for the first order reaction, the half-life is 30 mm. I don't know what mm is. Half-life is 30 minutes, I guess. Time taken for 75% completion of the reaction. This is the first order reaction. half-life is 30 minutes, very easily we can say that for 50, like suppose we have 100 reactant molecules, for it to become half you needed 30 minutes. Now 75% completion means 25 of reactant is left. So which means half of 50, how much time it will take? Same, 30 minutes. Next, a first order reaction has the rate constant 4.6 into 10 to the power minus 3 number of correct statement from the following are. Reaction completes in 1000 seconds. Reaction will never be completed. Okay, this is reaction completes. This is not a correct statement. It will keep on going till infinity. 100% completion will not be attained. Reaction has a half-life of 500. Let's see, 0.693 divided by 4.6 to 10 to the 3. So on doing the calculation, comes out something 150 seconds. So this is also a wrong statement. The time required for 10% completion is 25 times the time required for 90% completion. This is a first order reaction. So 10% completion. The equation is something like RT is equal to R naught minus some factor into ln concentration at time t divided by concentration at initial. So concentration at time t for 10% completion. So basically it is for 10% completion, time is proportional to ln t by naught. So t for 10, t for 90, ln a naught into 0.9 divided by a naught into 0.1. So 9. So it's not 25. This is ln 9. It's not equal to 25. This is also incorrect. Degree of dissociation is equal to, this is correct. Fifth one says the rate and the rate constant have the same unit, and it's incorrect. Then for certain chemical equations, x is equal to y, the rate of formation of product is plotted against time. Correct statements. Overall order of this reaction is 1. If it is 1, then see, it is the formation rate of formation of product is attaining a constant value. So it is not seen in first order reactions. Order of this reaction can't be determined. We'll see in region 1 and region 3 reaction is of first and zero order respectively. So see, rate of formation of product is directly proportional to time. This is what is happening in the first region, and rate of product is not proportional to time is in the third region. So both of them are different, and if rate is independent of time, then it is zero order reaction, and if rate is dependent to time, it is first order. Yeah, true, this is true. In region 2, odd reaction is of first order. Region 2 we can't really determine. Region 2, the order of reaction is in the range of 0.1 to 0.9. Yeah, this is correct. Like C and E is correct. Even overall order of the reaction, if it is an overall, it can't be determined. But since they have written just order, sorry, since they have written just order, we are saying that C and E are the correct statements. Next, for conversion of compound A gives B, the rate constant was found to be 4.6 into 10 to the power minus 5 liter per mole per second. Order of the reaction is rate constant is 1 by C. So for zero order reaction, it is just concentration by time. For first order, it is just time. Second order, it is the concentration into time. So yeah, this is by reasoning, we can say this is a second order reaction because rate constant is inversely proportional to concentration to time. Right. Next, compound A reacts with B following first order kinetics. Rate constant they have given. Time taken from A to reduce B from like time taken for A to reduce from 7 gram to 2 gram will be 7 to 2 gram. 2 by 7 log. What's the formula? I remember. Yeah, at constant volume. So yeah, time is equal to 2.303 by K log 7 by 2. So they have just multiplied the minus sign inside. Solving for this, you just write the value of K, put the value of K, put the value of log 7 by 2, multiply everything, and you get your answer. It's 623. Okay. Then an organic compound undergoes first order decomposition. If the time taken for 60% decomposition is this much, time taken for 90% decomposition, so time is proportional to log 80 by a naught, sorry, a naught by 80. This is the time. So T60 upon T90 is proportional to log for 60, a naught will be like 10 by 6 divided by log 10 by 9. Sorry, 10 by 1, 10 by 4, like it's concentration rate. So 10 by 4, it is log 10 is 1 minus log 4 divided by 1. So yeah, it's minus log 4 is 0.6, so it is something 0.4. The ratio is 0.4. Ratio is 0.4, so 540 is for 60%. On some time for 90% is 0.4. So for time completed taken for 90% completion is 4 1350 seconds. That is the answer. Next, the rate constant of the above reaction at 200 and 300 Kelvin are this the activation energy. So rate constants proportional to e to the power minus a by RT. Okay, so ln k is proportional to minus a to the power RT. They have given, so let's assume they have given rate constants. Okay, so ln rate constant for the first section is 0.03 divided by ln 0.05 is equal to R to R, you'll get cancelled. Minus 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 will also get cancelled. It will be EA2 by EA1 into T2 by T1. which is T1 is 200, T2 is 300. So log 0.03 by log 0.05 is equal to EA. Okay. Oh, so EA will get EA1, EA2 is nothing. EA will get cancelled. We have to solve it for each 10th question. EA is going to be the same. Let's see how they have solved it. This is, they have taken a ratio. Oh, just wrong formula itself. This is how they have solved. They have taken the ratio of the both rate constants, put it in the formula, multiplied everything, and they have got EA as 2520 joules. I got this wrong. Really sorry for that. Right? You can see the explanation here. It's quite clear. It involves a lot of like calculation, but it's clear at the end. Yeah. Now, physics option, and chemis option, analytical application of its option. This is surface chemistry. So we can like surface chemistry option. I'll just match it for you. This is the thing. Option 4 is correct, but you learn it in surface chemistry. The rate constant for a first order reaction is this. Rate constant, the time required for initial concentration to 1 by 32. 1 by 32 is 1 by 2 to the power 5. So yeah, 5 half-lives. 5 half-lives is 0.693 by 20 into 5, 4, 0.41, 0.17, 17 into 10 to the power minus 2. A and B are two substances. Radioactive decay is happening, which is following first. Radioactive decay is first order kinetics. Half-life of A is given, B is given. Initial concentration of B is 4 times of A. They both start decaying at the same time. How much time will it take for both concentration to be same? So half-life of A is 50 and B is 4 times that of A initially. So 4A, A. Let's see at 15 minutes. At 15 minutes, at 15 minutes, this will undergo 3 half-lives. So this will be 1 by 8 or A by 2. And in one half-life for this 15 minutes, this will also be A by 2. Yeah, so 15 minutes. Easy. The graph represents the following reaction. C6H5. Now, which graph represents this reaction? So concentration, so rate will, if it is a first order reaction, assume this is the first order reaction, rate will be depending on the concentration of reactant like this. Okay, above reaction is of zero order, half-life is 50 minutes, time taken for concentration of A to reduce to 1/4. So if half-life is 50 minutes, which means to reduce 1/4, yeah, I can tell you it's 75 minutes. Okay, but you can solve it like kt is equal to a naught minus a at t, and a at t is equal to 1/4 a naught by 4th. So kt is equal to a naught by 3, and you know that t1 by 2 is equal to a naught by 2k, and this has been given as 50. So a naught by k is equal to 100. A naught by K is 100. So 3T is equal to 100. T is equal to 100 by 3. So it is 66.66 minutes. So 67 minutes. Got it? Okay. So yeah, we have completed with the questions. We are finishing the class here. All the best for your JEE mains. Wish you all the best. Bye.